Okay, we did a pin junction introduction and Pn, put them together, and there will be a region. What's the name of this region? Depletion region. Forward bias. And the junction capacitance Cj go up or go down. Forward bias. Why? Is everybody getting that? So I'll let you talk about it, okay? All right, pin junction, because of what? The electrons are moving to left and holes are moving to the right. I'll let one of you talk about it, okay? I have a bunch of questions, okay? So let's take the turn. I want to do the first one, maybe from here, okay? All right, so I put a P and N, put them together to form a pin junction, and because of what? Electrons move to the left and holes move to the right. Concentration gradient, okay? And they diffuse to each other, to the other direction. And the region is called depletion region, you said it, right? And if I forward bias it, is the depletion region gonna be thinner or thicker there? If I forward bias it, is this depletion region being pushed thinner or being expanded thicker? Look at this, you got an anode here. The anode is gonna attract electrons, so it's taking electrons away to make it thinner or thicker? Thinner. Okay, as a plate, if you consider this as a capacitor changed from this to this. Is the capacitance getting bigger or smaller? C equals epsilon A over D. D is the distance, right? A is the area of the plate. It's going to increase because D is, you got a smaller D, which is result in a bigger C, right? Okay. And this one, if I add a metal plate here, it forms a diode, because metal pin junction, it becomes a diode. The IV curve for a diode, this is VI. VI here is considered as the voltage from P to N or N to P. So VI, if here's a diode, right? I'm using a VI. Is the VI considered as from here to here or here to here? Here to here or here to here? Which one? Left to right, right? So if you consider that this one is a regular diode in the real world, and so it breaks down, we have a pretty high negative voltage. But I'll let you draw the IV curve of it. What that looks like in the real world, not the ideal one, which has a built-in potential, for example, 0.7 volts. Breaks down. Is there a gap here? Yes, it's not perfectly zero amps. It leaks a little bit. And that's called saturation current. We're not going to talk too much about it here, but it's going to leak a little bit current in the other direction. And until a certain voltage, it's going to break down. And it's not reversible because this is not a, it's not a watt diode. It's not a Zener diode. Okay. And you can visually tell if it's a Zener diode or a regular diode from the look. Usually they have a different package for them. But when you guys are building a power supply module in the future, never pick up the Zener diode in the lab. Okay, I have seen so many students in the past having a circuit was sourcing components in the lab in the drawer. If they couldn't find a regular diode, they just pick up a Zener diode being used as a diode in the power supply module. Really embarrassed, the class. Maybe, I don't know, if you grab that little PCB and show it to the whoever interview you for the company for the job, they look at why you use a Zener diode over there. So this is a power supply module. I use it as a regular diode. It's ridiculous. Don't do that. Okay, it's not like I found a diode, I'm going to use it. You have to look at the data sheet, see if that fits the circuit board. For transistor, like NMOS transistor, gate, drain, and source. Why is called source? Yeah, it's a source of electrons. It's called drain. It's draining electrons. So the voltage between these two terminals is called VGS. Has to be larger than what in our process? VTH. No, VTH, threshold voltage, to turn on the channel. Turn on the channel doesn't necessarily running current in it. So turn on the channel, which means you got electrons being attracted at the bottom of the channel, staying there, being ready to be pushed. We don't have any current flow yet. So VTH in our case is 0.8 volts. What is VGS over IDS? So we always look at the IDS. Is there a current flow in G and S? I mean DC current flow from G to S. No, it's dielectric material in the middle. No, it's not a conductor. It's not moving. But AC, because it's a cap here, it's a capacitor, parasitic capacitance. It's a cap. So if you apply AC voltage, it considered as a short circuit for AC signal. But DC, there's no DC current at all. That's why it's slightly lower power consumption compared to the BJT transistors. BJT transistors is basically just an NPN, three junctions or three pieces of semiconductors, N-type, P-type, and N-type, and you put a metal plate here, and you put a metal plate here and here to form a transistor. That's the old version, but still being used in the power modules. Can run more current in through it as a part of the power module, and also cheaper. But cannot modify, cannot make it in 5 nanometers like the ones we are using, the FinFET technology being used for the smartphones, CPUs, can integrate like 10 billion transistors on one chip. They have to use CMOS technology instead of BJTs. So this is called bipolar junction transistors, or BJTs. And the symbol looks like this. Probably have seen this in a lot of places. It runs a little current in here and amplifies it in this way. So this is B, base, collector, emitter. So emitter emits current, runs current through it, and you have to run a little IB here in order to make an IC. It's getting amplified. So IC equals to beta times IB. So it's getting amplified. It's a current to current. It's a current source. No, it's current controlled current source. Current controlled current source. For the BJT transistor, we're not going to do that too much of it in this class. It's going to be covering analog. So this is the BJT transistor consume a lot of power, a lot more power compared to these ones, because this one is only using electric field across this dielectric material, the gate, to control the current. See, it's a voltage controlled current source. It's a VGS controlled current source. This guy, you got a current flow into the channel, which is IC. It's a current controlled current source. So it's an IB controlled current source. So whenever you are not running an AC signal, it constantly has a small current, which is IB, flowing in the circuit. If you are not turning it on, or even you turn it on with the VD, there's no DC current flowing to the gate. That's why it consumes less power. Okay, no details, just to talk about this really quick. Okay, this is a voltage control current source. Do you know what the IV curve looks like here, from starting from 0, for example? VGS, like this, and this is VTH. Okay, so what if we sweep VDS instead of VGS? Saturates, and this voltage is called VDS sat. So VDS comma sat. It's a VDS here, the voltage at VDS, the saturation voltage for VDS. And after that voltage, this the current is not changing too much anymore. So we are looking at VDS in this case. And so to understand this better, we have to look at the cross-sectional view of it. So if you apply a VGS to it, ground S, and this is VGS, this is N plus. So it attracts electrons to the channel. But if you add a VDS to it, because this is a plus, right? So it's a anode of the power supply. It's being directly shorted to the N plus terminal. And you got electrons being attracted to the channel. What's going to happen is the electrons will move here, will move into the power source, the VDS, because it's anode. It's going to attract the electrons to it. And this layer used to be this, but when you turn on VDS, it probably the layer looks like this, connect to the middle of the N terminal here. Okay, and that because you have a stronger electric field, so current will increase almost linearly at the very beginning. But whenever it reaches VDS set, which is here, it saturates the current. Why? Because this layer will connect it to the corner here. It's doesn't have a capability to keep increasing the current anymore. And this state is called pinch off. Connect the corner. So for example, here's the channel, right? I got electrons. And when the channel looks like this, okay, when it looks like this, it's called pinch off. And it saturates the current. We don't have a microscope to look at the electrons, how the layer moves, but it moves that way. If you Google it, pinch off of CMOS, you'll see a little animation, how that works. So the layer moves up and then saturates. You can watch that animation. That's how that works, okay? If I ask you to draw VDS versus IDS, can you draw it? If I ask you to draw VGS versus IDS, can you draw the curve? If I ask you to draw VI versus I for regular diode, can you draw it like this? Okay, basics of semiconductors. Since we know that if you put a P and N together, there will be a CJ, junction capacitance, the junction capacitance, and it decrease and increase depends on the voltage you connect to the pin junction. So we did a N-well resistor in the first week or second week. It's a P stop. Do you have a pin junction here? Yes. Right? It formed a pin junction. But since this is grounded, is there anything wrong with it? If I want to use this thing as a resistor, it's just a I just want to use this guy as a resistor, right? But if it's, I mean, if this forms a pin junction, is there anything wrong with it? Is it going to affect anything? Pin junction is a diode, right? And I ground the diode. It's like I have a diode here, and I ground the anode, and then I got a resistor on the top. How that works is like a potentiometer. Does it affect anything? Is it going to affect the resistance or something? Is it going to affect the ways that we want to use it as a resistor? Where's the negative voltage? Oh yeah, no, this is the lowest. I ground it, but you consider this as the lowest potential in the circuit. So there won't be any more negative things anywhere else. Mm-hmm. That's right. Yeah. But any other than that, anything else? It's gonna work. I put on the tutorial, it's gonna work, right? Otherwise, I won't put on the tutorial unless you lay it out. So there's nothing wrong with it. It's just a pin junction. There won't be any current flow into it because I short the piece up to the lowest potential in the circuit. And now it makes sense why we have to do it. Why we have to short the piece up to the lowest potential in the circuit, because there will be some parasitic diodes embedded in the circuit, right? Whenever the P sub, the P terminal of the diode is not the lowest, there's a possibility that there will be current leaking into the circuit. Okay, you want to reverse bias the parasitic diode all the time by shorting the P sub to the lowest potential in the circuit. Okay? So there will be capacitance. So because this is a cross-sectional view of it, so you can imagine capacitance will be here, here, or ground, here, here. What are these capacitance? What are they? You have a pin junction, right? So pin junction is going to form what in the middle? Depletion region in the middle, like this. There will be a depletion region here. Okay, so that's a depletion region, which is a capacitor. And the N well is a resistor at the caps. So when you use it as a resistor, what's going to happen? I got to pause here. What's going to happen with N well? So it's not an ideal resistor anymore, right? Yeah, or in another word, alternative way to say it. There will be a time delay, right? You got a resistor, the capacitors, it's going to delay the signal. What's a constant? So if you have a very simple RC circuit, like a pulse, right? And you know that if you did it in the first lab, you'll see something like this, right? You're measuring 50% of the voltage and measure the time difference between them. So if you have an RC circuit like that, the time delay equals 0.7 RC. So there will be a time delay for the unwell, and it's called distributed RC delay. And how to calculate it. So in the textbook, 1 1 over RC. 1 over RC? That's in frequency domain. You are saying 1 over 2 pi RC. That's a cutoff frequency. So RC is time, right? 1 over RC is frequency. So 0.7 RC. But it got so many capacitance. You got a huge resistor. How to do it? Can you find one capacitance somewhere? It's kind of difficult to do that. Because the resistance is everywhere. It's like you have a resistor here, and the caps are here. No. So it won't be this. It's not being shorted to the terminal, it's being shorted to everywhere in the middle of the resistor, right? So there's a way to model it from the textbook. So you split that resistor into smaller pieces, okay? Because all the caps are shorted to the in the middle. It's just everywhere. And we definitely cannot use an infinite number of caps for the calculation. So we just divide it into smaller pieces. And we learned how to divide the big thing into smaller pieces in one of the labs for the calculation and in one of the quizzes as well. How do we do that? No. We divided a big resistor into smaller ones, right? Or we build bigger resistors using smaller pieces. And what is that called? Shear resistance. So we divide the big one into smaller squares as one single resistor. What about the caps? Yep. Can we divide the caps into smaller ones? Can we do that first? So you have a bigger cap here, right? Bigger cap. Can we divide it into smaller ones? Is that the legit way to do it? If we have a big cap and then we divide it, so just looking at the area and divide it into smaller ones in parallel. Can we do that? Just make sure they have the same area in total. Are they the same capacitor? For example, C1, C0, right? C1, C2, C3, CO equals C1 plus C2 plus C3. Can we divide into 3 capacitors? Yes, because parallel capacitors are being added together. Imagine that they are just connected plates, right? What I mean? Okay, a big cap, you cut it into small 3 pieces, but you short the terminal into 1. It's still the same capacitance. Why? Because C equals epsilon A over D, right? If A0 equals A1 plus A2 plus A3, definitely C0 equals C1 plus C2 plus C3, because C1 is epsilon A1D, it's the same D here, plus epsilon A2D plus epsilon A3D. More space efficient, what does that mean? Why? You are not changing it. I don't think you are changing it, because the areas the footprint will be eventually added together, right? So it's going to achieve the same capacitance. It's just the same area. It's not changing anything. So now we are not designing a capacitor, because these are parasitic capacitors. We're not changing anything. This is not a capacitor, definitely. This is a resistor, has some undesired embedded capacitance we have to consider, because it's causing the delay. Now we have to know, if we design the resistor, we are not intentionally making a capacitor or getting some time delay, but it's going to causing time delay because of the parasitic capacitance. So we're trying to understand how much delay it's going to cause in order to take that in consideration for our digital design. So we cannot make our circuit too fast because of the delay, right? For example, your time delay, here from that's the input, right? Okay, and that's your output. It delayed the signal horribly. And then are you able to use a digital signal? For example, I want to increase the clock frequency to run the CPU faster. Okay, can I use a digital signal look like this? A clock like that? Definitely not, because your time delay is even larger than the frequency of it. So what's going to happen is, if you have an input like that, what's going to happen for the real signal, for the output of the NWL, is if you see here, that's the input, that's the output. So it only reaches this point, and then it's going to discharge it. So what's going to happen for the output is, all right, so if you know the time delay for the NWL resistor you put in the circuit, you got to know the there's a limit for the frequency of the clock you can run. You can put it into the circuit. So it's important.
We can try and minimize that time delay by making the width smaller, right? And that's going to decrease the overall area.
But it becomes longer, right? Or minimum width, yes. So we use the minimum width, right? Okay. Yeah. Yeah, smaller capacitance also it takes smaller area. Make sense? Okay, what's next? What's the logical next? No clue. What's the logical next? Should be. How to calculate the distributed RC delay, right? We know there's a delay, but how much is it? You know there's a delay, but you don't know how to calculate it. Not going to help. You want to know how much is it. So the way to model it is, for example, this is the input of the NWL, and you divide it into small r squares. It's r square. It's a sheet resistance. So every r square, if you have a specific width, for example, that's a minimum width, and as a square, it defines, if you have a width, as a square, you define the length as well, right? So you know exactly the footprint of it. Is that correct? If you know the width, you got the length because it's a square, okay? If you have the width and length, you know the footprint. If you know the footprint, you got the capacitance. Because D is a constant. You cannot change D. If you want to change D, you have to give a lot of money to TSMC. I want to change the distance between the plates. Deposit a thicker silicon dioxide in the second layer, that I have to purchase another photolithography machine from SML for another $1 billion. And the chip is sold for $1. Yeah. So it's called C square, right? This R square. Again, so we know this. We know C square if we know width and length, right? So we know the footprint. C equals epsilon A over D. Depends on how many you have in the circuit or the resistance of the NWL. And here's the output, V out. That's V in. What is this? What is this? The NWL resistor. A model of the NWL resistor. So the way we do that No, let's label this is A, this is B, this is C, this is V out, right? So the textbook calculated the time delay for each and then added them together. Does that make sense? That's how you calculate the time delay, because V into A, there's a certain time delay, and A to B, there's a certain time delay, and B to C, there's a certain time delay. So A to out, you just add the delay together, will be the final time delay. Okay, so TDA equals 0.7 what? Yeah, R what, C what? Mm-hmm. And these are constants, you know it. TDB equals no, it's actually the textbook did the way that you calculate it, because it's always from the input. So from input to A, you got a delay. Input to B, you got another delay. But only considers this cap. Because only the capacitor is giving a nonlinear result, which is a delay here. So for TB, the time delay at B, it is 2 R's and 1 C. 0.7 2R square. You look at this circuit, you got 2 R's and 1 C. So 2R times C square. So TDC equals, it's a RC circuit in series, so you got 3 resistors added together and but 1 cap. So TDC, the C, time delay C is 0.7 times 3 times R square times C square. And eventually TD out equals 0.7 times, we use L here, L. Why do we use the L? So this is 1, right? 1, 2, 3, and L times R S. What L stands for? But yes, length. Why we use the length here? That's how many squares you have. It's a number, that doesn't have a unit, it's just how many of them. You got 1, 2, 3, 4, you put all the little squares together to form a resistor, right? That's how many of them you have in here. 1, 2, 3, and eventually you got an L here. So TD overall equals TDA plus TDB plus TDC plus TD out equals 0.7 R square C square 1 plus 2 plus 3 plus L. And what is it? And there's an equation for this station here, right? 0.7 R square C square times L times L plus 1 over 2. This equals this. If L is pretty big, like over 10. If L is over 10, this little 1 here becomes insignificant. Agree with that? Let's don't say 10, let's say 100. Like L is 100. So it becomes L times L plus 1, which is like 100 times 100, 101. It's pretty much 100 squared, right? So when usually L is 10 or something, I don't know, over 10 at least, okay? So 1 is not significant. In that case, this is pretty close to 0.7 R squared, C squared, L squared over 2. Any questions so far? No? Good? Let's do a quiz. Kidding. Does that make sense? Any questions? So this equals what? TD. Eventually. I got 2 here, cancel. I got a 0.35. So it becomes 0.35 R squared, C squared, L squared over, no, just L squared, right? 2 is canceled. That's a time delay for the unwell. Let's look at one example. Estimate the time delay through 0.25 kilo ohm resistor made using an unwell with a width of 10 and length of 500. Let me see, what did I put here? I could calculate it. I think you can calculate it, but there's a square. Assume a 10 by 10 square of unwell has like 5 femtofarads of capacitance. Do you need me to let you know the sheet resistances, or you can calculate it from here? Sorry, this is 250K. So before we move forward, let's think about this for a little second. So we want to calculate the time delay, right? So for the time delay, we have to look at the equation here, or the equation here on the top. This is the constant. We need to know the length, R squared and C squared. Okay? Let's look at R squared first. Do we know R squared here? Depends on how I want to define the square. Define the width first, one dimension first. Then you know a square, the dimension of the square. Okay? What's a good dimension for a square for this case? 10, right? 10 by 10 is the unwell's capacitance, right? It's like 10 by 10. And also the resistor, the unwell resistor is a 10 by 500, which means it's probably trying to let you use 10 as a width. Okay? So what's the dimension of the square? What's the dimension of the square of one square of the n well? 10 by 10. So how many squares do you have for this resistor? 50. Okay? And what's the resistance for 50 squares being put together? What's the resistance? Over what? This is what? R square. Or the sheet resistance. And what is it? Done. C square, given. Done. L, 50. Done. So TD equals 0.75 times 5k ohms times what times what? Five what? It's a moment to test your English. What is this? Femto. Femto, right? Femto. First time my English is better than yours. My Chinese is always better than yours. So it's 5 times what? What's the last one? Right? Yeah, 50 square, right? No, we already have 0.7 divided by 2, so we got 0.35. Right? So what's here, right? So we cancel 2, and this becomes 0.35. Okay? And calculate it. So what's a unit? So k ohm, you have to convert into 10 to the third power ohm, the standard unit. Either a unit for this guy. No, it's a constant. There's a unit for this guy, which is ohm. Is there a unit for this guy? Yes, femto. No, Fahrenheit. Farad. What is Fahrenheit? Fahrenheit is temperature. Farad, sorry. Right. Femtofarad. What is this? No unit, right? Just a number. How many? Pieces, maybe? So eventually the calculated number is 21.875 nanosecond, or 21.875 10 to the what second? Equal 9. Okay. Any questions by far? So in the lab, did you use a C5 model file or use the models file? Which one did you use? You use the models, and that you can. It's a C5 or models. If you use models, I mean it's fine, but in the future, make sure you use C5. So the transistors are, the model's name are called NMOS instead of N_YU. Okay. And what I heard is NMOS instead of NMOS, like American English. So if you are in an interview, don't say NMOS. NMOS, PMOS, NMOS, CMOS, not CMOS. Okay. So let's see, C5, which is a 500 nanometer technology. It's called C5. C probably stands for CMOS. I don't know. I'm not really sure. It was a over 50 to 60 years old technology. Used to be free from a company called MOSIS. What type of company that is, MOSIS? That's the not MOSIS, MOSIS. It's a service company, but we're not using this company because it's not free anymore. And so before 2018, it's actually the second year I came here. When I was teaching analog, we actually fabricated a chip with MOSIS, which was free. So every single student got a chip, 5 copies. They put in the package for us. But now it charges $20,000 even for the 60-year-old technology, C5, $20,000. And for smaller, they do have smaller technologies down to probably 22 nanometer, and it charges way more than the one we are using, which is Muse. About somewhere around $6,500, I think, for one design. For the TSMC 180 nanometer technology. Smaller technology compared to this one, so it's more modern, but still sort of obsolete already. We're trying to make the memory files from this design kit, and the memory file has to be compiled on a Solaris machine. Runs so it's a Sun machine, the Sun. It's called Sun computer, and runs a Solaris 8 operating system. This is a 20 to 30, 25 probably years old computer tower and operating system. Nobody's still using that. And because this technology is sort of old, so TSMC is not updating their memory compilers with Windows or new Linux. So we have to either use a virtual machine to run Solaris operating system on Windows, or we have to buy a Sun machine. That's what I did. $900 to buy a 25 years old machine, and have to use their mouse and keyboard, which has a really weird, I forgot the name of it, connection. And the keyboard itself is $250, and the mouse is like $150 just for to put the machine together is over $1,000 just for compiling the memory for this technology. Okay, just let you guys know. I put a lot of efforts to make it work. Why we have to use 180 nanometer technology? Because anything smaller than that is the price. We cannot afford the price to fabricate it. That's the only thing we can afford, which is doable in the colleges or university in the US. You can see it's just so many factors to down to this conclusion. This is the only way to make it work. That's why we are probably the only university in Colorado are doing this for students. Just so challenging. That's why the U.S. government has realized it and giving $200 billion for the Chip and Science Act. Because there are a lot of people are using that for fundamental research instead of IC design, which is really disappointing.